In Chapter 6, we'll look at the ADC and its features. In the lab, we'll use an ADC and a sample sequencer to measure the outputs of the 3-axis accelerometer on the educational booster pack. The microcontroller features two ADC modules, ADC 0 and 1, that can be used to convert continuous analog voltages to discrete digital values. Each one of those modules has 12 bits of resolution, can operate independently, and can execute different sample sequences. You can sample any of the shared analog input channels, single-ended or differential, and you can generate interrupts and triggers. The microcontroller has two A to D converter modules, sharing 20 input channels. Each one of the modules can make single-ended or differential input measurements, has an on-chip temperature sensor, has a maximum sample rate of 1 million samples per second, uses the external voltage reference and ground pins for its voltage reference. There are 4 programmable sample conversion sequencers per ADC, and the part has separate analog power and ground pins. The ADCs have a very flexible trigger control and can be triggered by the software, the timers, the analog comparators, the PWM, and any GPIO. Hardware averaging is available from 2 to 64 times in powers of 2. Each module has 8 digital comparators and 2 analog comparators per device. Both modules are DMA enabled. The analog to digital converters collect and sample their data using programmable sequencers. Each sample sequence is a fully programmable series of consecutive samples that allows the ADC to collect data from multiple input sources without having to be reconfigured. Each one of the modules has 4 sample sequencers that control the sampling and data capture. They are identical except for the number of samples that they can capture and the depth of the associated FIFO. In order to configure a sample sequence, the following information is required for each sample: the input source, whether the mode is single-ended or differential, whether or not to generate an interrupt, and whether this is the final sample in the sequence. Each sample sequencer can then transfer its data from the FIFO independently using a dedicated DMA channel. We'll be using the Educational BoosterPack Mark II in the next couple of labs. The board features a 128 by 128 pixel color TFT display connected to the SPI bus, a 3-axis analog accelerometer for measuring motion, a no-contact infrared temperature sensor connected to the I2C bus, an ambient light sensor connected to the I2C bus, an RGB LED connected to GPIO pins, a microphone, buzzer, servo connector, joystick, and several push buttons. In Lab 6, we'll enable and configure the ADC and sequencer to measure and display the values from the analog accelerometers on the educational booster pack. Once we see that that is working, we'll add hardware averaging to smooth the changing values, and then we'll graph the results in Code Composer Studio. Finally, we'll switch over to using ROM peripheral driver library calls and note the code size difference.